CS111 is an introduction to computer science. But what is computer science? Hal Abelson at MIT, one of my advisors, was fond of saying that computer science is neither about computers nor is a science. It's not about computers in the same way that chemistry is not about test tubes and Bunsen burners and biology is not about microscopes. Computers are a tool that are used in computer science, but they're not the focus of the discipline. And it's not a science in the same way that chemistry and biology are sciences, where we're performing experiments to find out laws about the physical world. We're trying to understand something that's more abstract, something about information and knowledge. So what is computer science? Well, computer science is the study of imperative or how-to knowledge, as distinguished from the declarative or what is knowledge of mathematics. For example, we know in math that the square root of 9 is 3 or negative 3 because if we take those numbers and square them, we get 9. That's declarative knowledge. Imperative knowledge is if I give you a number, how do you go off and find the square root of it? And it turns out there are ways of doing that. As an example from real life, if I ask you how do you get from the Science Center to Tower Court, you can give me directions. And those directions are telling me how to do something, how to get from one point to another. And there might be multiple ways of doing that. Or if we want to make chocolate chip cookies, there's recipes for doing that, sets of instructions that we can follow. And in the area of programming, there are computational recipes, which are known as algorithms, which are the way that we go off and describe programs or computations. And an awful lot of this course will be spent coming up with and evaluating these computational recipes or algorithms. Here's a quote from Hal Abelson and Jerry Sussman that I think is very deep. A computer language is a novel formal medium for expressing ideas about methodology, not just a way to get a computer to perform operations. Programs are written for people to read and only incidentally for machines to execute. This quote has been a guiding light throughout my journey through computer science because it emphasizes that programs are about communicating knowledge between people, not just about ways of getting machines to do things. And to prove that these mechanical computers are not the essence of computer science, we can just look back to the history of computer science and back to the 1930s and 40s, where a lot of the seeds of computer science were planted by giants like Alan Turing and Alonzo Church, and they didn't have any kinds of mechanical programming or computing machines. In fact, the word computer back then meant people who performed computations. Now, another aspect of computation is something called computational thinking, which is an idea that Jeanette Wing has written nicely about. And it says that computational thinking goes beyond programming and is really a way of looking at the world and has a level of importance that's on the same lines as reading, writing, and arithmetic. We'd like you to read an article by Jeanette Wing on computational thinking, which is in your Google Docs folder under the CS111E reserve. In this course, we're going to focus on 4 big ideas: abstraction, modularity, divide, conquer, and glue, and models. And these are going to be themes throughout the entire course, and let me say a little bit more about each one. The first idea is abstraction. And the idea is that we can take a very complex system, and in order to understand it, we can hide away a lot of the details and only present the essential details that matter. Here's a concrete example. Most of us know how to drive a car, but we don't necessarily know how a car works. So there's a whole lot of details about the engines and the pistons and so on that we don't need to know to drive a car. All we need to know is if you press the gas pedal, it goes. If you press the brake, it stops. And this is a beautiful abstraction. And we have players in an abstraction. So in this case, we have the user or client, or the people who are driving the car. here on the left. On the right, we have the implementers or designers, the engineers who have created the car. And in any system, between the implementers and designers and the users, we can establish something called an abstraction barrier, which hides the details that the user or client doesn't care about. And we can provide what's called a contract to the user or client about how to use something. So in the case of the vehicle, the contract is press gas pedal, go, press brake, stop. And so much of our lives are guided by abstraction. So for example, when you go and turn on the faucet on a sink and water comes out, that's a beautiful abstraction. When you go plug an electrical device into a wall socket and electricity is provided, that's a beautiful abstraction. When you go to a store and just buy things on the shelves that are in cans or bottles or what have you, that's a beautiful abstraction. And we wouldn't be able to live our lives today without these kinds of abstractions. And I'd like you to think tonight about how many abstractions are involved in your life. And in this course, we're going to explore abstractions in the context of computer programming, and we're going to see how you can take some very complex algorithms or computational recipes and hide them inside of methods in Java in such a way that the details are hidden and yet you can still use them. And so that's a big idea. The second big idea of the course is modularity. And here's the notion of modularity. We have these complex systems that are built out of parts called modules. And these modules are good to the extent that we can mix and match them to build other kinds of things. So let me give you some examples of modularity that I really like. So we have modularity in toys. So here we have some Lego bricks. And they are modular because we can take the bricks and we can click them together in different ways to make different kinds of structures. It turns out the Lego designers are really, really clever. And they made different kinds of Lego bricks. So these are called Duplos. They're the intermediate level bricks. They're sort of traditional Legos, which are much smaller. They're made for older kids. And then there are these things called Primos, which were made for really young kids. And the Lego designers were so brilliant that they figured out a way that you could connect all these together. So for instance, we can connect a Primo brick with a Duplo brick, and we can connect the Duplo brick with regular Lego bricks. And then amazingly enough, we can connect those back to the Duplos, and everything connects together. So that's a beautiful example of modularity. We have a lot of modularity with electronics. So for instance, here's my cell phone, my smartphone, and here's a cable that plugs into it, and it has a USB attachment. And I can now connect this to my computer, and I can download pictures off my phone, or I can also charge the phone. And if I don't happen to have a computer to charge the phone, I can click it into this unit, and then I can put this into a wall socket and charge the phone that way. That's a beautiful example of modularity. Here's a third example of modularity that comes from a birthday party that I had recently. My wife purchased a create your own banner kit, and it had in it letters like C and O, and it had a way of connecting the letters together to form longer strings. So for instance, we can connect the letters LYN to form Lin. And the beauty of this banner system is that you can reuse the letters to make other banners. So it turns out my wife's birthday is 2 days after mine, and we just changed the Lin to Lisa, and we had a birthday banner for my wife as opposed to me. And that's a beautiful example of modularity. Our third big idea in the course is that of divide, conquer, and glue. And this is a problem-solving strategy that is patterned after Julius Caesar's wartime strategy of divide and conquer for taking over a foreign land. And in the area of problem solving, here's what it means. We have some big problem P that we're trying to solve. And we can break it down into smaller problems. Call these subproblems P1, P2, P3, and P4, and so on. And then we can solve each of these subproblems to get sub-solutions, S1, S2, and so on. And then if you glue the solutions together appropriately, you get a solution S to the whole problem P. So let's be concrete here. Suppose the problem P is we want to hold a birthday party. And that has many parts. So P1, subproblem P1 might be we want to invite some people to the party, so we have to send out invitations. And problem P2 might be going off and buying presents. And problem P3 might be baking a cake. And problem P4 might actually be hosting the party. The divide, conquer, and glue strategy is recursive, so we can take a problem like P3, which is baking a cake, and we can divide it into parts. So to bake the cake, we need to collect the ingredients, we need to put the ingredients together, and then we need to bake them. And then each of those has subparts. For instance, collecting the ingredients, one of the ingredients might be flour, we have to find flour. So we have to solve the problem of finding flour. At some point, we consider a problem so simple that we can just solve it. So for instance, in terms of buying flour, or rather in terms of acquiring flour, we can just go to the store and buy it. That's a solution. But there are other solutions. We could plant wheat seeds, we could grow it in our garden, we could grind the wheat into flour, and that would be another solution. But at some point we consider a problem so simple that we can just solve it and go from problem to solution. And then we take our solutions and we glue them together. So in the case of a cake, after we've assembled the ingredients and we've combined them together and put them into the oven, that sequence of operations leads us to a cake, and then we have a solution, which is a cake to our problem of baking a cake. And in the context of programming, we will see divide, conquer, and glue again and again. It's one of the main themes we'll see over and over throughout this course. Our final big idea is that of models. Whenever we have a complex system, we need to develop simple models to understand the complex system. And in the case of this course, one of the complex systems we are trying to understand is the Java programming language and how Java executes programs. And to do this, we will establish something called the Java execution model, which explains how Java programs are executed. And we will use this model throughout the course. That ends this portion of the screencast. The last portion of the screencast is more about Java and some Java programming that we'll be doing.